Okay, so what we're going to do is talk about intermolecular attractions. Well, let me make some points here that are kind of interesting to know about. So as you know at this point, the behavior and properties of different kinds of gases like oxygen, nitrogen, and argon can be described by a set of laws like Boyle's law, Charles' law, and the ideal gas law, and so on. And these laws predict the behavior of gases very well, but the interesting thing is these laws that we use to predict the behavior of gases are not perfect. And if you were to take more chemistry classes, you would learn a little bit about how these gases at times can deviate to some degree from these laws. But at room temperature and pressure, these laws do a very good job explaining the behavior of gases. On the other hand, one thing we have learned is there's really no set of laws that explains all the different kinds of liquids well, nor is there a set of laws that explains all the different kinds of solids well. And so you might wonder why this is the case. And so what we find is that gas laws work really well in explaining the behavior of all gases because all gases kind of look the same. They all are molecules that are all kind of far apart and they're moving very fast. While solids and liquid, the molecules are relatively close together and you have different kinds of attractions between the molecules depending on what the molecule is. Okay, so what I want to do is kind of generally point out here as I kind of sit on the board, when you have ionic compounds, you have strong interactions between the ions, and they're so strong this explains why the melting points of the ionic compounds are so high. Now compare that to covalent compounds. Here, the attractions between the molecules in covalent compounds are much weaker, and so they have usually lower melting points. But let me just kind of focus in on the ionic compounds just for a second. And so if I can decrease the slide. So here what we're going to be doing is looking at an example of an ionic compound. This ionic salt, which again is table salt, which is sodium chloride, and so it's a solid at room temperature. So I want to talk a little bit about why ionic compounds are solid at room temperatures using sodium chloride as this example. So you can imagine sodium chloride is made up not of neutral atoms but of ions. So there's the positively charged sodium ions here in red, and they're the negatively charged chloride ions here in green. And so they are all stuck together. And so if you have billions and billions and billions of these positive negative ions clumped together, that might give you an individual tiny crystal. Now, one of the things you might remember earlier is that there are attractions between the sodium positive ion and the negative chloride ion. And these attractions are very, very strong. So to indicate the attraction, I'm just going to kind of highlight this area between the ions here. So these are called ionic bonds. And so between the ions here, you have these ionic bonds, and the bonds are strong and they hold the ions together. And so you're going to need a lot of heat to break these strong bonds. And so the heat available at room temperature is not nearly enough to break these bonds. And so you really have to get this sodium chloride aggregate or crystal up to 801 degrees Celsius before some of these bonds break. And so what happens is some of these bonds between the ions will break at that temperature, 801 degrees Celsius. And then what happens is the ions are kind of free now to move around each other like this. They can kind of flow around each other. So at 801 degrees Celsius, the ions are kind of flowing around each other, and now the sodium chloride is in a liquid state. So what I basically said for sodium chloride applies to other ionic salts as well. Most, if not all, ionic salts are solids at room temperature because we have bonds that are strong, ionic bonds, that are holding the ions together. And you need very high temperatures to get the compound into a liquid form. So if I can increase the slide. So on this next slide, I kind of mentioned here in sentences what I just said in words at the board. Okay, now what we're going to do is we're going to focus on covalent compounds. So we're going to focus on those. And so, very importantly, while ionic compounds had very strong ionic bonds between the ions in the compound, here with covalent compounds, you have weaker forces. And the weak forces occur between the actual molecules of the covalent compounds. These weak forces are relatively easy to break, and oftentimes, if you're at room temperature, that will be enough energy to break some of these weak forces to allow, say, a solid covalent compound to become a liquid. Now, in some cases, as it turns out, as you'll see, with some covalent compounds, you only have extremely weak forces between the molecules. And so these very weak forces only come into play when you're at a very, very, very low temperature. And so that would be enough maybe to solidify the compound. But if you warm it up, the compound to any degree, it will become a liquid, and by the time you get the compound to room temperature, it will boil off, all the weak forces will be broken, and you'll get a gas. So there are relatively weak intermolecular attractions between molecules and covalent compounds. The problem here, there are different amounts or levels of attraction between the molecules depending on the type of molecule they have. So the different molecular compounds behave differently. Some covalent compounds have low melting points, like say way below 0 degrees Celsius, and some may be a little bit higher, say between 0 and 100 degrees Celsius, but it doesn't even come close to the melting point of ionic compounds, which can often be, say, 800 to 1,000 degrees Celsius. So the reason for this range in the melting points of covalent compounds is because there are different kinds of attractions between the molecules which you need to be aware about. However, we have divided these attractions that occur between covalent molecules into 3 different types. And so here is a chart that's actually available in your book. So the first type of attraction that can occur between covalent molecules is called a dispersion force. And so the book calls it a London dispersion force. So London in this case is not a reference to a European city. Instead, it's a reference to a man named Fritz London who described these forces back in the 1920s. And so one of the things you'll learn is that all molecules have these dispersion forces. However, that being said, they are extremely weak forces, and you need very little heat to break them. And so here are some examples of molecules that will have these dispersion forces. But again, all molecules that exist have these dispersion forces. Now, there are molecules with some stronger forces between the molecules. These forces are called dipole-dipole interactions. They are stronger than dispersion forces. They're of moderate strength, and you will find that they tend to occur in polar covalent molecules. And so here are a couple here. But then there's a subset of these molecules that have these dipole-dipole interactions that have a stronger kind of interaction, which is called hydrogen bonding interaction. And so this will be even stronger than the dipole-dipole interaction. And we'll talk in more detail about how you get hydrogen bonds in a minute, but you maybe already know that water is an example whose molecules have hydrogen bonds between them. Now, just a note here, when you're looking at the relative strengths of these forces, the dispersion forces are the weakest, followed by dipole-dipole, and then hydrogen bonding are the strongest. But when we say strong here, that doesn't even compare to, again, ionic bonding. So the forces between the ions are very, 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 I'm writing 4 V's here, very, very, very strong. So again, these interactions, even the strongest one, hydrogen bonding, it doesn't really even compare to the strength of ionic bonds. Okay, so here we're just kind of have this nice chart that reminds us when you have compounds that only have these dispersion forces, they have only weak attractions between the molecules, and therefore it doesn't take much heat or energy to break those bonds, and therefore molecules with only dispersion forces have extremely low melting and boiling points, since it takes so little energy to break the bonds between the molecules. On the other hand, molecules with dipole-dipole interactions, these molecules have stronger interactions than the dispersion forces that they'll also have. And the dipole-dipole interactions are, again, a little stronger, so it takes a little bit more heat or energy to, say, get to a melting point or a boiling point. And then a subset of molecules that have dipole-dipole interactions have hydrogen bonds, and those interactions between molecules which have hydrogen bonds are a little bit stronger. And so that will increase the boiling point and the melting point of that compound even further. Okay. So moving on. So first off, I want to talk about dispersion forces. And so